So I hope you're all settling down in your seats and ready for our afternoon session. And for the start of our afternoon session, we're going to have MIT's own Josh Tennenbaum, Professor of Brain and Cognitive Science. And without further ado, I'll have Josh go because we're running right on time, which is remarkable. But to keep that going that way, I'll keep it short.
Okay, is this microphone working? Yeah. All right. So thanks. Is there a weird echo? It sounds weird. No? Is it? Oh, how about this? Okay. Thanks to Michael and Bob for inviting me. I feel a little out of place here, although pretty much all the morning speakers said that. But for me, it's because I'm not a linguist. I'm not a computational linguist. I'm not a psycholinguist. I really don't know very much about language, I have to be honest. In particular, while I've done some work related to language for a while, it's been more on the lexical side, for example, modeling word learning. And whereas here I'm going to talk a little bit about syntax, and the program of research I'm going to talk about, which is in collaboration with Amy Perforce. Amy is here somewhere, right? She's a grad student in our department, and also Terry Regier of University of Chicago, is pretty preliminary, but I'm very interested to talk about it with you and get your feedback on it. Since I'm not really coming from the language community, let me say a little bit about where I am coming from. The kind of research we do is aiming to understand, in some sense, how the mind of both adults and children solve everyday problems of everyday versions of classic problems of induction. So, throughout cognition, wherever you look, you see places where we seem to know more than we have any reasonable right to know about the world, places where we come to abstractions, generalizations, models of the world that just go far beyond our sparse, noisy, limited experience. Lila mentioned a case which I've also done some work on of, say, word learning. How do you learn what a word means? Like, how do you learn that the word dog refers to all dogs from just seeing one or a few examples of that almost infinite set? Another classic case that, say, comes from the philosophy literature but is active in current cognitive science, causal learning. How do you learn causal relations just from observing patterns of events? Or we're also quite interested in larger scale systems of knowledge, like intuitive theories of physics or psychology, which clearly go way beyond our limited experience in the world. And from that point of view, the study of acquisition of syntax is a very interesting problem of that same class. The goal of our work is to try to come up with general purpose computational tools for understanding how people solve these problems of induction and how they solve them so successfully. And this kind of domain general approach is somewhat different, I guess, than the way most linguists proceed, where they've carved out a particular system or organ of the mind and try to study what's distinctive about that mental organ. I think that's a very compelling approach, and I'm not trying to argue that some kind of general purpose statistical framework or any other kind of framework is going to explain away or get rid of that, but rather it's complementary. What we're going to come up with here are tools for studying the nature, use, and acquisition of knowledge, just the classical questions that Chomsky introduced to all of us. Another way to think about it is to say what we're studying here is something not like a mental organ, but like the biochemistry of the mind, right? It's a certainly legitimate approach to study mental organs, but it's also a legitimate approach to look for general laws. In our case, they're not biochemical laws, but more informational laws that might govern how all these organs might work and develop. So the kind of questions that we're interested in are basically questions of knowledge. If we want to understand how inductive leaps are possible, it must be because there's some other knowledge in our head, some more abstract knowledge that guides and constrains our inferences. So we want to know what form that knowledge takes, how it guides inductive inference, and how it itself might be acquired. And the kind of tools that we're going to develop, which I'll apply here to some analyses of syntax, are there's several principles, but I'll just highlight three. The idea of doing Bayesian inference, which is a particular kind of statistical inference that I'll introduce to you in probabilistic generative models. The idea of defining probabilistic models not over what you might be used to thinking of if you are thinking of basic probability, not just sort of numbers or vectors of features, but very structured representations, actual knowledge, objects like graphs, grammars, schemas, predicate logic, maybe functional programs, for instance. And a particularly important idea for today's talk, the idea of defining hierarchical probabilistic models, models with multiple levels of representation linked by probabilistic representations. And by doing inference in multiple levels of this model, we can start to address in an integrated way questions of inference and acquisition of knowledge. So let me just illustrate these ideas in a linguistic setting. And this is just a cartoon diagram. It's kind of extrapolated from one in this nice review paper by Chris Manning and Nick Shader. Here's a way we might try to think about language from this framework. We could have a multi-level system of representation where the levels are linked by generative relations. So each level generates objects at the level below. And in that sense, it's very compatible with traditional linguistics. The extra thing is that these are probabilistic generative relations. So instead of we're not just saying what objects can be there at the level below, but which ones are more or less probable. And for example, if say at a lower level, we might have a probabilistic expectations of, take a word, shoot. We might have some expectations of what sounds are likely to occur in our data if somebody's uttering the word shoot. That would be this conditional probability here. Or we might have some expectation of, say, given a grammar, if we define it as a probabilistic grammar, so it assigns probabilities over possible phrase structures, then it might tell us which phrase structures are grammatical, but also maybe which are more or less to be expected. The advantage of having this hierarchical probabilistic model is then we can use Bayesian inference to address inference problems at all of these levels, either individually or jointly. So what we mean here by Bayesian inference is just combining top-down and bottom-up constraints that take the form of these conditional probabilities. So let's say you want to infer what word somebody hears from observing some speech signal. So you have the bottom-up information, which is just captured by this conditional probability, or we'll call it a likelihood of some speech sound given possible hypotheses of the utterance. This is what we're trying to infer. What was the word? But there might be some top-down information, say coming from a syntactic analysis based on words you've previously heard. And speech recognition is full of these kinds of contextual effects. And Bayesian inference just says, take these probabilities, combine them, multiply them, and renormalize, and that gives us a kind of ideal belief distribution over possible words we could have heard that incorporate top-down and bottom-up constraints. Or if you want to do Bayesian parsing, then the top-down constraints are now coming from the grammar. The bottom-up constraints are maybe coming from the sequence of words, and we're again going to look for the sort of most likely parse of that sentence. You can even push this up to questions which we usually call acquisition. So what you could think of as Bayesian grammar learning, where we now are going to form hypotheses about possible systems of rules describing the syntax of the language. The bottom-up information comes from, it sort of filters down from the actual direct observations, or filters up rather, through various parses. So you could say once, at least if we've preliminarily identified the parses of a bunch of sentences, those provide data for our bottom-up data for our possible grammar hypotheses, and there might be some constraints, and at least under one interpretation of UG, it's the source of these constraints. So the reason to work with these kind of hierarchical probabilistic models defined over structured representations is to give us an integrated way of treating all of these problems. And one thing we know about child language acquisition and adult language processing is all these problems have to be solved together. So it's very appealing, at least to me, to have some kind of integrated architecture for doing this. I just want to emphasize, kind of in light of something Chris was saying before, that how important are the probabilities here? Well, for us, we're more interested in the scientific questions, although we sort of take an engineering approach to the scientific questions. We think of what we're doing as a kind of reverse engineering. So we're not actually that interested for most of the things we want to reverse engineer in the specifics of probabilities. We're not building these probabilistic models because we think the core phenomena of language are probabilistic. Rather, we're using it because it gives this very general, powerful, and rational inductive inference engine. As we'll see, it gives us tools for doing things like Occam's razor, balancing complexity of hypotheses and fit to the data, which any rational induction mechanism is going to have to do. And so it's for that purposes that we're using this probabilistic approach. Okay, just to give you, again, a sense of the larger context, we're interested in these tools because they can apply across many areas of cognition, not just vision. So there's a lot of excitement. Again, it's sort of an old idea revisited of thinking about image interpretation as a kind of parsing, but now in ways that are actually working on real images using probabilistic grammars in this sort of a hierarchical Bayesian setting. In other work we do, we apply these tools to problems of concept learning and word learning, or, for example, causal learning, where causal learning now isn't just the identification of causal links purely from correlation, but conditioned in a top-down way from abstract theories of how the world might work. You can even apply this to thinking about action production and action understanding. But I mean, that's fairly far afield. I just want you to get a sense for the generality of these ideas, or at least where we'd like to go with them. So for today, I'm going to talk about syntax. And in particular, I'm going to talk about what might be up here. The place where we're coming from is the classic poverty of the stimulus argument, and I guess that's why I'm talking here. Michael already did a great job of introducing this, so I'll go through this very quickly. the idea of a stimulus poverty argument is to start off from observing that children in the course of acquiring language know things about, say, complex, rare constructions that they don't have any or maybe very little direct evidence for. And in learning those, they seem to avoid maybe simpler, tempting, but false hypotheses that would otherwise explain the data, somehow going just right for the more subtle, correct hypotheses. How do they do this? Well, they must have some more abstract constraints that make it possible. And the tradition in generative linguistics is to call that UG. We've, like many people in the cognitive science literature, probably been a little bit too obsessed with the Oxford case. It was one of the things that we started thinking about here, although it doesn't really play a big role in the work that we're doing. But just to remind you about this and to illustrate the point, the idea is if you want to explain why is it that, say, from fairly simple data, like these simple declaratives and interrogatives, children come to something like the correct rule of say, moving the auxiliary and the main clause to the beginning, the kind of rule that would allow you to form a complex interrogative like, is the girl who is sleeping happy, as opposed to this incorrect one, which would be licensed by maybe an a priori simpler, you might think, linear rule. Well, you've got to explain some additional constraint that would prefer rules like this over rules like that. And one way that this has been put in the literature is positing that the abstract knowledge is that syntactic rules are defined over hierarchical systems of phrase structure rather than, say, the linear order of words. So it's a constraint about grammar being something like this, hierarchical, as opposed to something like this, linear. And then you would posit, okay, well, that's part of UG, and that would somehow innately constrain and condition the acquisition of syntax at the level below. It would give you a prior. Okay? Now, there's been lots of arguments in the cognitive science literature that are sort of objecting to this, saying, well, if you use the right kind of statistics and maybe even fairly simple surface statistics like n-grams, all the problem goes away. You don't need these inductive constraints. And that's not what we're arguing here. We're quite convinced, because we study problems of induction and we really try to get things to work. You need inductive constraints, and the idea of hierarchical phrase structure is a very powerful one. The question that we're interested in, though, is what form these constraints take and how do they get there, right? And in particular, we're interested in the question of must they be innately specified as part of a language-specific module in the brain, or under what circumstances might they be somehow learned or acquired? I mean, what we mean by learning and acquisition here, you'll see that's subtle. But might they somehow be acquired without having to innately specify them as part of a language organ? And really, this is all about the interesting content of stimulus poverty arguments is that they provide a powerful tool for diagnosing what, in fact, might be part of the innate endowment in any one domain. So what we're asking is, how does that logic work, and when are we really justified in doing this? Classic stimulus poverty arguments, at least the ones that get known in the broader cognitive science field, aren't usually very formal. They're often kind of informal, and that means anybody can have whatever view they want of them, and you can argue endlessly about them. But we think there's something to be gained by taking a somewhat more formal approach. So the claim that we'll present here is, and I've sort of highlighted the crucial words, that it seems to us to be possible that given the data of child-directed speech and certain kinds of innate domain general capacities, then an unbiased ideal learner who isn't particularly biased towards hierarchical phrase structure rules as opposed to, say, linear grammars, might be able to identify the hierarchical phrase structure of language, thereby using this as an inductive constraint to guide acquisition of particular pieces of syntax. And it's possible, then, that this inductive constraint doesn't have to be innately specified as part of the language faculty. So just to be crystal clear, we're assuming two important kinds of domain general capacities. Then these are, as far as our analysis goes, these are still domain general. One is the ability to represent grammars of various different types, including hierarchical and linear ones, the kind that you might use to form hypotheses about these sentences, but also the ability to evaluate these hypotheses using the engine of Bayesian probability. Just to sort of foreshadow where we're going, you could say intuitively the answer to how this could be possible is making the inference that a hierarchical phrase structure grammar, as opposed to some alternatives we consider, provides a more explanatory count of the data that a child sees in the sense of, say, optimizing some trade-off between fit and simplicity. And this is a very old idea in linguistic theory as well as in other places where you study induction. So, for example, from Chomsky's earliest writings on the topic, he presents basically the idea of an evaluation metric in terms of simplicity which you could measure as a kind of description length. So he says, as a first approximation to the notion of simplicity, we here consider shortness of a grammar as a measure of simplicity. And then once you fix a notation for the grammar, so you now have a vocabulary in which you can measure the description length, the criteria of simplicity governing the ordering of statements, or hypotheses in some order of preference, are as follows. The shorter grammar would be the simpler, and that among equally short grammars, the simplest is that in which the average length of derivation of sentences is the least. And you could see further developments in classical linguistics, such as the logical structure of linguistic theory, as kind of extending this idea, and they're applying it to the idea of a multi-level generative system, which looks maybe something like the picture I showed you at the beginning. Now, just to again set some of the context for this work, there's a long history of ideal learnability analyses, and so many of these have been mentioned in previous talks: Gold, Horning, Englund. Bob has done some very fundamental work here, and others. And I just want to say a little bit about how what we're doing is different from all of this. Typically, so, Horning did his work in a Bayesian setting, but most of this work has been done in some kind of a simplicity-based idea where you have an evaluation metric in terms of simplicity. Sometimes that simplicity metric winds up being somewhat arbitrary. Other times it just winds up being uncomputable. Sometimes it winds up being identical to Bayes. So for those of you who are familiar with certain kinds of minimum description length, you will know that those can be kind of equivalent to the kind of Bayesian analysis we're talking about here. But there's several advantages that we see to this Bayesian approach. It gives a rational, objective way of trading off simplicity and fit as in Occam's razor. It's not to say that it doesn't have important points of arbitrariness, and we'll talk at the end a little bit about where linguistic theory comes in helping to resolve that. A key thing is that it prescribes ideal inferences from any finite amount of data, unlike some other kinds of approaches which are really about learning in the limit. And it naturally handles ambiguity, noise, missing data, and all sorts of things that people, particularly who are trying to engineer language systems, care about. Another difference is that, and this is one that's pretty clearly in our negative, is that most of this work tries to prove formal theorems, whereas for us, we're mostly just doing empirical explorations of computational models. We'd like to be able to prove formal theorems if we can, but it's because of the third thing that we're interested in that's quite difficult for us. Maybe the most interesting difference of what we're trying to do is, in contrast to previous analyses, which have typically considered either highly simplified languages like a palindrome language or some kind of idealized corpus where you have an infinite amount of data and you just assume if you wait long enough, every grammatical sentence form will show up, and also in a probabilistic sense where you would assume that the empirical frequencies of what shows up is given by the true grammar if it's probabilistic. That's all highly idealized. If you think about the problem the child faces, you have only a small finite sample of sentence types, and the language might be very complex in terms of the range of sentence types you could see. You're only seeing a small fraction of them. The distribution might depend on all sorts of other factors that don't have anything to do with syntax, semantics, pragmatics, performance, and so on. So what we're going to be doing is focusing on a more sort of preliminary empirical exploration of learnability from a realistic corpus. Another way to view the landscape of possible results is to say most traditional learnability analyses are considering what an ideal learner of some sort could get from an ideal corpus of some sort. Whereas, ultimately we all want to know what can a real child learn from real data. If this is what we had, then we would really have a powerful tool for trying to diagnose what goes in UG from looking at behavior. But we don't have that. So we're taking a step towards that by looking at what an ideal learner might be able to learn from realistic data. And there's another tradition which I'm not sure, perhaps some people will talk about later, in which, for example, Ken Wexler has done some work in this direction, and Partha and Bob, where you try to have a kind of a psychologically realistic learner, but see what it might learn from some kind of idealized corpus. Both of these, I think, are interesting. The reason why, at the moment, I'm more interested in this is partly it hasn't been so much the focus of previous work, but also it's not at all clear to me what is a realistic learner. It seems a lot easier to go and measure the data that a child actually sees than it is to know what are the actual true computational constraints inside the child's mind. We can discuss that later if you're interested. So here's the actual model that we're working with. It's this sort of three-level probabilistic generative model where at the bottom we have data, some observed sentences from our corpus. We're then interested in a specific grammar, and we're also interested in a type of grammar, which might be, say, a hierarchical or a linear grammar or some other type. And we're going to be doing Bayesian inference jointly over these two higher levels of abstraction, the grammar and the type, given the data. And Bayes says we should be interested in the product of three probabilities. The first one we're just kind of going to get rid of because we're interested in what an unbiased learner could learn. I mean, it might turn out that you need to have some a priori bias for some types of grammars than others. And that would be, if it turns out that you need that, then we would have really learned something deep about UG. But we're interested in how far you can go without that as a way of diagnosing whether we need to have, say, a bias towards hierarchical grammars. The remaining terms, which we'll call the prior and the likelihood, the prior being the probability of having a specific grammar given some type of grammars, and the likelihood being the probability of the data that we observe given the grammar. These will capture a notion of simplicity and fit to the data. So I'll just illustrate this schematically and then show you, but not really go through a little bit of math. Here's a schematic illustration where this two-dimensional space represents, say, all possible strings that could be uttered. Only a subset of that is the content of your language. And you observe some finite, sparse sample of the language. So there's some region here that we'll call the language, and a grammar is a way of picking that out. So here are some possible language hypotheses. And you could see how they maybe vary on these dimensions of simplicity and fit. So maybe the simplest grammar we might posit would just pick out, say, this circular blobby region. That's very simple. A much more complex one would say, pick out a very complicated region which involves drawing a bounding curve around every single point we have, right? So clearly in terms of simplicity, this seems like a better one. But in terms of fit to the data, well, in some sense, this one is better because this one makes very strong predictions about what you're going to see, and sure enough, that's exactly what you see. Whereas this one kind of says, well, you could sort of see anything, and it just sort of happens that you've seen these things. So it doesn't provide very strong predictions. Whereas a model like this, which is probably what you saw intuitively when your perceptual clustering mechanism when I showed you this picture at first, probably formed something like two groups like that, is kind of the optimal trade-off maybe between simplicity and fit. Almost as simple as this one, almost as predictive as that one, but better in combination. And Bayes just formalizes that. Probably it should be pretty clear how the idea of likelihood or the probability of the data sample given the grammar or given the region, how that formalizes the idea of fit, right? The idea being that this one here, because it predicts only a very narrow range of possible sentences or data points, assigns them very high probability. It's quite sure that that's the kind of sample you're going to see. Whereas here, it's very low likelihood because there's sort of this kind of you could basically almost see anything in this space, and it's sort of kind of a coincidence that you just happen to see the dots clumping up as they did. It might not be so clear how probability can capture the prior, but that's important, really critical for what we're doing. Just to be clear again, what's going on is not some a priori specification saying, independent of the data, I prefer simpler models over more complex ones. So the probability over the grammar type, which in this case would be the number of regions, is uniform. Where the preference for simplicity comes in is in the probability of seeing this particular grammar or any particular grammar of a certain type. A way to think about it is to think the prior probability is the probability if you hadn't seen the data, you're just going to sample a grammar from your type or a set of regions, particular regions, curves on the screen from the knowledge that you say have 13 regions. So you can see why that would be very low in this case. If I just said draw 13 regions on this thing, what is the chance that you would draw exactly those 13? Well, infinitesimal, and particularly much smaller than this. If I just said draw a region, well, it's not that improbable that you draw something kind of like that one, right? So that's the notion in which the prior, in particular, the probability of a model conditioned on some more abstract model class captures the notion of simplicity, penalizing more complex models which require more arbitrary choices over those which don't. It's also quite interesting to see how this relates to another classic idea in language learning, what's called the subset principle. Again, something that a number of people in this room have really done all the seminal work on. So what is the subset principle? It's this approach to language acquisition to deal with the problem of learning from positive evidence only. And it's most developed in syntax, but other areas of language and cognition too. And the idea says, well, to avoid positing an overly general grammar that you're never going to be able to recover from without negative evidence, always choose if you have multiple hypotheses, always choose the one which is the smallest in the strict sense. That means it's a subset of all of the others. So in particular, if we were considering these two hypotheses here, the subset principle would tell us, choose this one. It's a subset of this one, right? And indeed, that would be correct here. But the problem with just using the subset principle as far as it goes is that it would also, if this grammar were in our hypothesis space, it would tell us actually that we should choose this one because it's actually a subset of this one. But doesn't seem right in this case. And you could solve that problem by just ruling that out and saying, well, UG says that that's not in the hypothesis space, right? And then the subset principle is okay. But the problem is that you could imagine data sets in which, well, you might learn that. So for example, if you happen to see a lot more data and it clumped just like that, then you might say, oh, okay, that is the grammar, right? Or if you had only a smaller amount of data, this might be the right inference. And the Bayesian version of Occam's razor is going to appropriately balance fit and complexity in a way that's sensitive to how much data you have. And that's going to be critical when you're trying to learn over a long period of time and starting off with very small samples and getting more samples. Now, when we actually apply these to grammars, there's neither time, probably, nor patience to go through the details of the math. The way we'd assign a prior, which is a probability over grammars of a certain type, is basically the same approach that Horning used, which is to have a kind of a metagrammar. And it's, in some sense, a probabilistic version of the classical linguistic approach as well. It's a procedure for generating grammars or sets of rules. And you make a bunch of choices, and each of those choices, if there's multiple ways it could go, you have probabilities. And in some sense, the more choices you have to make, the lower the probability of making a particular string of choices in the particular way that it came out. That was what was penalizing these more complex models here, and the same thing will penalize more complex grammars. So the result, the bottom line, is that grammars with more rules and more non-terminals will tend to have lower prior probability. The likelihood is going to capture the fit of the grammar. Again, there's some technicalities, but basically this is the probability of the corpus data being generated from the grammar, and that requires us to take the product over all sentences of the probability of generating that sentence, and each sentence might have multiple parses, so we sum over all the parses of the sentence. And what a probabilistic grammar does by putting probabilities on production rules is really assign a probability to a parse. The bottom line is, all other things being equal, grammars that assign long derivations to sentences will tend to be less probable. That's a sort of, again, a classical linguistic idea. Remember, that was there in the first quote I showed. But also grammars that generate sentences not observed in the corpus will be less probable because they waste probability mass. So this is the probabilistic version of the subset principle. And it's going to be critical because basically what this is saying is if a grammar overgenerates, then it's wasting probability mass on things you don't see, and you want to penalize it. But it's critical because one of the things we want our grammar to do is generalize beyond our experience. So we'll see how this trade-off plays out. Now we're going to use this general framework to analyze various different grammars in various different types. So some hierarchical grammars and some linear grammars. And in all cases, all of these models all the grammars we're going to consider are clearly oversimplified. But we're just trying to make choices that are representative of these larger classes that you might develop in a more sophisticated linguistic theory. And then that's future work is to extend this to richer syntactic representations. So for hierarchical grammars, we'll just choose basically vanilla context-free grammars as our exemplar. There's obviously oversimplified models of syntax in all sorts of ways, but they seem to be a reasonable first approximation if you're just interested in basic aspects of phrase structure and not more sophisticated aspects of syntax. We consider several different kinds of context-free grammars. Basically, we start off with one that's about the simplest thing you would come up with for the corpus we're working with if you'd just taken a basic class in syntax. But then we consider variants, which basically add in additional productions, making the grammar more complex, but allowing it to fit the data better so that we can consider within this class how it navigates the spectrum of complexity and fit. For linear grammars, well, there's many different kinds of things you might consider, and we consider grammars which span a wide range here. At one extreme, you could have what we call a flat grammar, which basically just memorizes the sentences in your corpus. It fits exactly, but doesn't compress at all. There's no, it's sort of just as complex as the corpus itself. I would see the extreme points here as just sort of benchmarks. They're not any kind of a serious proposal. At the other extreme is this one-state grammar. It's kind of like a unigram probability model. It basically can accept any sentence, but is extremely simple. A little bit more interesting are these finite state or regular grammars. Again, we just choose a classic exemplar, but this isn't meant to be, you could imagine more sophisticated linear grammars. Again, there's a trade-off between we consider grammars which make different trade-offs between complexity, number of rules, and how well they can fit the data. We also, although I don't have time to tell you any of the details, have considered many different ways of trying to come up with these grammars. So we've considered, for all the grammars that we work with here, we've considered local search algorithms for trying to refine them and improve them, such as the Stolkian-Omohundro Bayesian model merging approach, if you're familiar with that. So it's a way of sort of taking any of these grammars and trying to make a bunch of local improvements to it to see if you can come up with something better. We've also explored algorithms for automatic grammar construction, and what I'll show you is just basically the most representative best grammars of each type that we found. But just so you know, while I'm only going to show you results from a few grammars, there's been many, many grammars of these sorts that we've analyzed here. The data comes from ChildNS, corpus of child-directed speech. Is that 10 minutes? Okay, good. Child-directed speech. And we've made a couple of simplifications here that are also things one would want to extend in future work. One simplification is just to replace each word by a syntactic category. So the kinds of data consist of that the algorithm is seeing are strings like these. These are the actual sentences they were transcribed from. Another simplification, and in some sense this is also a gesture towards traditional linguistics, because we're really interested in a grammar as a way of describing the possible types of sentences you can see and not really capturing details of the probabilities in the empirical frequencies in the corpus, we're taking as our data the sentence types and not the sentence tokens. So there's sort of one example of each of these sentences here. And we've also been starting to look at more complex kinds of probabilistic models, which are very interesting ways to try to sort of integrate type and token information based on the idea of adapter grammars, which Mark Johnson and colleagues have developed very interestingly, but we haven't really gotten very far on that yet. So here are some results. These are results on the full corpus of something like 2,300 sentence types, which corresponded to about 20-some thousand utterances. And note for reading these graphs, these are negative log probabilities, so that means lower is better. Okay? And I'm graphing for 5 different grammars, 2 context-free. Oh, sorry, I tried to be all clever and color code, but I made these green instead of blue. All right, well, you get the idea. So I'll tell you. The blue ones are the regular finite state grammars, and the green ones are the context-free ones. And we're showing the priors, likelihoods, and posteriors. And as might not be too surprising, if we have an induction framework that balances complexity and fit, and we've tried to explore a bunch of grammars across that spectrum, well, the best one we find is one that's somewhere in the middle. It's this one here, which is the more complex context-free grammar. That's this green bar here. But it doesn't win on either the prior or the likelihood. So basically, the context-free grammars are all simpler than the regular grammars as measured by the prior, and this one is the least simple. It has more production rules. When you go to likelihoods, it goes the other way. The regular grammars have lower likelihood. And this is maybe the most interesting thing, or might be slightly surprising if you haven't thought about this kind of analysis before. You might think, well, if context-free grammars are more right, why do they fit the data worse? Right? That's what this means. This means that they fit the data worse. They make poorer predictions about what you're likely to see. And that comes from this thing I was telling you about before, that basically these grammars overgenerate more. They have more, well, part of it is because they have recursion in them, but they can generate more things. And those just didn't happen to show up in the corpus. But that's just the flip side of their strength, which is we're counting on them to generalize appropriately. So just as a sense of how these grammars might generalize, we can go back to an example like the case of these ox-fronted complex interrogatives. It turns out in this corpus that there are in fact no complex ox-fronted interrogatives. So there are no sentences like this, where there's 2 auxiliaries in a question, one of them at the beginning, like that. There are some simple declaratives and interrogatives and a few complex declaratives, not even very many of these. And what it turns out, and this is hopefully what we'd like to see, is the grammar which does best in terms of its overall fit to the corpus also does the best on this particular phenomenon, or does the right thing, namely these context-free grammars correctly can generate the correct form of the complex interrogative. They don't generate the incorrect form, whereas, say, the other grammars don't do the right thing. They either generate both or neither. And they can do this because, they've seen 0 direct evidence for sentences like this, but because they have abstract structure, things like noun phrases, which they can get from the rest of the corpus, inductive support for. And that's sort of for free then. You get to do the right things here. So that's the key idea. And in some sense, it's reconstructing most of the basic intuition in the original version of this argument in the poverty stimulus literature, which is that by having the right kind of inductive bias, the idea of hierarchical phrase structure, you can make generalizations which you have no evidence for on the face of it. The only difference is that in some sense that inductive bias has been learned rather than specified as part of the initial state. It's also interesting, although not so interesting that I'm going to waste my last couple of minutes on it, so I'll skip that. Or do I have 5 minutes? Or okay, well, then it's enough. It's interesting enough. It's interesting to say how much data do you need to make this inference. And what you can see is just actually taking one file, like the first file from this corpus. It's about 90 minutes worth of sentences. Even that is enough to infer the right type of structure. If you just look at the end final results, the posterior probabilities of the hierarchical grammars are higher, even with just a very small amount of data. It turns out it actually, again, as you would expect from this Bayesian Occam's razor, it actually chooses the overly simple one. It chooses the simpler context-free grammar, which ultimately will wind up not being the right one for the whole corpus. But it's learned the more abstract knowledge that the right way to describe the right type of grammar is a hierarchical grammar as opposed to a linear grammar. So just to conclude, I'll conclude with just some remarks about poverty of stimulus and then more generally about the relation between all the fields that we're interested in here. What we've given is, you could think of it as an alternative or a variant on traditional linguistic nativism. We've argued or sort of concurred that hierarchical phrase structure, for example, is a crucial constraint on syntactic acquisition, but perhaps it need not be specified innately as part of the language faculty. It's possible. We're not saying this is how children actually do it, but it's possible for an ideal learner to infer this inductive constraint from child-directed speech if that learner comes equipped with some certain domain general capacities. There's still clear nativism here, right? These are innate domain general capacities, but the key is that they're domain general. And that's the twist on the traditional poverty of stimulus argument. Again, really what this is getting at is we're trying to formalize these arguments and then use them as a tool to diagnose what has to be innate or what is more or less plausibly part of UG. There's many open questions, which I don't really have time to go into, but they're really big open questions. We have to ask, how close have we come to finding the best grammars of each type? How would these results extend to richer representations of syntax, or trying to jointly learn other levels of linguistic structure, like syntactic categories? And then what are the prospects for any kind of computationally tractable or psychologically realistic learning algorithm to approximate this ideal learner? There's also some more general issues in here, which I don't think I'll go into. But this idea that you could, in a sort of a top-down way, learn abstract knowledge is very different from the traditional empiricist bottom-up view of abstraction, right? The idea that in traditional empiricism, that abstraction comes from learning a lot of concrete stuff and filtering it all together, and gradually abstraction accumulates. Whereas here, what we found was that the more abstract knowledge about this domain could be learned sooner. And it's very interesting to try to apply that analysis to many other domains of cognitive development, to try to ask, well, in what cases are these sort of core constraints guiding maybe even infants' inductive inferences, what are the cases where those might or might not be learnable? And a bunch of other projects in our group are exploring these. The thing I'll just close on is just trying to address the stated proposition of the workshop. In one of the announcements, Bob and Michael sent out this hypothesis. They said, we want you to consider the hypothesis that statistical approaches should work within the framework of classical linguistics rather than supplant it. And I find myself being mostly in agreement with that. I might suggest a minor variant. Classical linguistics should work within the frameworks of statistical approaches rather than ignore them. All right, I thought I had to say something provocative. Here's a better version. And a more reasonable one, right? That really these classical linguistics and statistical approaches have much to gain by working together. And we've tried to illustrate a little bit of that here, but just what are the general lessons we can draw? Well, classical linguistics is all about mapping out hypothesis spaces. But statistical inference gives us more powerful techniques for evaluating these hypotheses in rigorous and powerful ways, using large-scale, realistic corpora and whole grammars, rather than just, say, small fragments of languages and grammars. This idea was an ideal in the early days of classical linguistics, like the LSLT days, right? And that was one of the key features of, as Chomsky laid it out, of his approach to grammar as opposed to previous structuralist approaches, which were more about this bottom-up approach. But at least in the poverty of the stimulus literature recently, it's been a bit lost. And I think it's time now to bring it back. In particular, these Bayesian statistical approaches might be particularly worth investigating because of the features I talked about. They sort of are a nice way to handle Occam's razor, and they're well suited for learning from real data sources with small finite samples and perhaps noise. They fit naturally, as I've tried to show, within a multi-level generative system, again, a classical linguistic idea. And there's a lot of recent progress on the computational and AI side that might actually make these ideal learnability analyses have some hope of being realized practically. The long-term benefits are that really what I've already said, this idea of trying to formalize these poverty, the stimulus arguments, or more generally, techniques for making inferences about what should be, what has to be, what might be part of UG, based on looking at the language environment that children have. And I think that kind of clarity is much to be gained. There's other benefits, like I think trying to end my time. Okay, well, there's lots of other benefits. Thank you.
Exactly one question, and I see the gentleman in the corner. I'm horrified to learn that I'm asking the only question, but I guess that way it will be the best one. I like all this stuff, and I've done probabilistic stuff myself before, but when I see something like this, I'm always curious and sometimes troubled by wondering where the explanation is. That is to say, in your discussion here, you seem to be saying that the best thing to do is to combine Bayesian statistical methods with classical linguistic constraints. So where is the explanation? Is it in the Bayesian treatment of the regularity, or is it in the constraints of classical linguistics? So maybe I could frame my question this way. Which would you rather have? Classical linguistic constraints and a crummy program for dealing with regularity, or good principled Bayesian statistics and a crummy theory of the linguistic constraints?
Yeah, I mean, I guess I would say that those represent just sort of different formulations of these questions here. I'll go with this formulation, which is I think that's sort of a false dichotomy. And while we've made some progress in both machine learning and linguistics, a lot of progress in both areas, we haven't made as much progress as we'd like because of being forced to choose in that way. I don't think we should have to make that choice. What I tried to show, for example, because I sense you might be skeptical about, or I can sense how you might answer that question. You might be skeptical about the value of having the right kind of statistical inference engine. Just go back to the very toy example I drew with the dots and the circles, right? And comparing what I was saying to the subset principle. So the subset principle was, about 20 years ago, a state-of-the-art rational ideal learner analysis, right? The basis for a lot of good work. But you can see a problem that it might give. If you applied even to that simple case, if you want to explain why, in the first case I showed you, right, this one here, this one, why, given these dots, don't you choose that hypothesis? If you're a subset learner, your only option is to say rule it out a priori. That means assert as part of UG that it's not there. And of course, then there might be some data or experience like this one from which you'd actually want to be able to learn it. And what this really reflects is that these two things interact, right? If you're going to make inferences about UG from observations of what people learn or so on, if your learning algorithm is in some sense too weak, then you might wind up putting too much into UG. So you really have to have these two tools working hand in hand in order to make progress about the questions I think we're all interested in. Thanks.